This presentation is basically an introduction to energy methods. We're going to start first of all by considering the various forms of energy. There's chemical energy, stored energy in oil that we can burn, or chocolate bars that we can use to give ourselves energy. There's electrical energy, nuclear energy, solar or heat or sometimes thermal energy, sound and light energy. And the energy we're particularly interested in this presentation is mechanical energy. Many other forms of energy to consider, but considerations such as tidal energy or wind energy, they tend to be forms of mechanical energy where kinetic energy is transferred into electrical energy. So let's consider mechanical energy. There are actually three types of mechanical energy to consider, but only two we'll review in this presentation. The first relates to potential energy. That has a formula of mass multiplied by gravitational acceleration multiplied by the height from a particular datum. And that's energy due to the position of an object in a gravitational field. For example, if we take a datum at the bottom of the man's feet here, then the dumbbells have potential energy relative to that datum, relative to that height. The second form of mechanical energy we'll consider in this presentation is termed kinetic energy. That formula is a half multiplied by the mass of the object multiplied by the velocity squared. And that's energy due to motion. We can use energy to calculate, for example, the velocity on impact of a toolbox. Shown here, this is a drop from the man's hands onto the floor. There is a third form of mechanical energy known as strain energy, but we're not going to consider that within this presentation. Here's a couple of scenarios where potential energy is transferred into kinetic energy. Considering the scenario on the left here with the downhill skier, if we take the datum, say at the bottom of the mountain, then the skier will have potential energy relative to the datum at the top of the mountain. As the skier travels down the mountain, the potential energy will transfer into kinetic energy as the velocity increases. Here, the man who's about to experience a push off the top of the bridge here has potential energy relative to the datum at the bottom of the bridge. So from his stationary position at the top of the bridge, as soon as he's pushed off the bridge, his potential energy will convert into kinetic energy and he will have some velocity on impact as he hits the ground. So what we're considering here is transfer of energy from potential to kinetic, and that's one of the considerations we'll be reviewing in this presentation. As you already know from a previous presentation on work done, because work is energy of course, the unit of energy is the Newton meter, which is also known as the joule, capital J. And for reference, a joule is enough energy to power a traditional light bulb for 1/60th of a second. So let's consider mechanical energy and just the forms of potential energy to kinetic energy. We will also use later in the presentation the principle of conservation of energy, and that states that energy cannot be created or destroyed, but only changed from one form to another. So in reviewing energy, energy is defined as the capacity to do work, and energy and work are interchangeable. Sometimes we'll put work into our system and create potential or kinetic energy, and sometimes we'll extract work out of the system. So work and energy have the same units, as we mentioned before, joules. And note that both work and energy are classified as scalar properties. In the previous presentation, we considered the concept of work done. Just going to recap it here, as it's something we'll need to refer to in this presentation. In applied mechanics, work is associated with the movement of bodies from one position to another. In the diagram, we're showing a force applied to a car. That force is applied over a distance, symbol S, and work is simply the product of force and distance. So since movement of the body from rest requires a force F to be applied, and the change in position is represented by the distance shown as S, then work is defined by relating the force and the distance. So our formula for work done is simply W is equal to F multiplied by S. Just note that the force applied must be in the direction of the motion. Work continued. Imagine the person push starting the car shown on the right hand side that has a flat battery. We would agree that pushing the car 20 meters at constant speed is only half of the work done pushing the car 40 meters. Also, directly pushing in the line of the motion is more efficient than pushing in other directions. In other words, in this case, pushing with force F in the horizontal direction, the direction of the motion, is more efficient than applying the force F at an incline, because only the horizontal component of force F would produce work in the direction of the motion. The vertical component would push the car into the ground. So again, it's better to directly push the car in the horizontal with force F than push it on the incline. And the sooner a downward slope is found, the better. Okay, then we have the effect of gravitational potential energy to help us increase the speed of the car. Again, just to recap here in the exercise 3 on work done. In the first part of the exercise, a force F of 200 newtons is applied to a car, and the car moves through a distance of 10 meters along a straight line in the direction of the force. We've got to calculate the work done by the force on the car. In part 2, if the 200 Newton force now pushes a car of twice the mass over the same distance, what's the work done? And finally, if a car runs down a slope for a distance of 5 meters, in spite of a force of 200 newtons in the line of motion, which is applied to hold it back, what work is done by the force on the car over this distance? The answers are shown in the brackets here if you want to attempt this exercise, but we'll outline the solutions on the following slide. So here's the solution to part 1 of exercise 3. We're applying our 200 Newton force to the car over a horizontal distance of 10 meters. Work is simply defined as force multiplied by distance. The force applied, 200 newtons, the distance 10 meters. So the work done is 2,000 joules. However, if we consider the 200 newtons now pushes a car of twice the mass over the same distance, what's the work done? The work done is identical to part 1. In other words, the force is still 200 newtons, the distance in the direction of the force is still 10 meters, and so the work done is still 2,000 joules. So in other words, work done is independent of the mass moved. And that's a characteristic to note. And in part 3, we have the car runs down a slope, a distance of 5 meters, in spite of a force of 200 newtons in the line of motion, which is applied to try and hold it back. If we calculate the work done now, we notice it will be negative work done. Here's our scenario. Our motion is down the incline, but our resisting force is up the incline. So therefore, when we calculate the work done, the 200 newtons must be considered to be a negative 200 newtons. It's opposing the motion. This is effectively work out of the system. So the work done is negative 200 multiplied by 5. So it's negative 1,000 joules in this particular case. So from exercise 3, we can note that work is independent of mass, and it also can be a positive or a negative quantity. Positive is work into the system, negative is work out of the system. So let's consider mechanical energy. Mechanical energy is present in the forms of potential energy, kinetic energy, and also something called strain energy. All forms of energy are scalar quantities, so they have a magnitude, that's a size, but no direction. But as outlined in exercise 3 previously, the magnitude can be a negative value, so work can be a negative quantity. Let's consider our two forms of energy for this presentation. Firstly, potential energy. That's energy due to an object's position in a gravitational field. So potential energy, PE, relates to the energy that a body possesses due to positioning. So if a car engine hangs from a hoist 2 meters above the floor, if that's the datum, then it has potential energy relative to the floor. We must, whenever considering potential energy, specify a datum, and the datum can be taken anywhere in the system. It can be above the object, below the object, on the object. But I would encourage you to state the datum at the lowest point in the system. So in this case, with the engine hanging from the hoist, the datum would be the floor. Now we know that work done is force multiplied by distance. And we know that weight is actually a force that we calculate by mass multiplied by gravitational acceleration. So potential energy is essentially the force multiplied by the distance, that's the work done. And in this case, the force is mass times gravity, and that's multiplied by h, the height above the datum. So the formula for potential energy is simply stated as P is equal to mgh. Example 1 illustrates the use of potential energy. We have a pile driver, that's just a lump of mass effectively that's used to drive a pile into the ground when you're involved with construction. And the pile driver has a mass of 250 kilograms. We've got to calculate the potential energy in the mass when this pile driver is 8.5 meters above the pile, and that's shown in a scenario here. Here's the pile driver with a mass, and it's a height, 8.5 meters in this case, above the pile that we're pushing into the ground. So from the question, the mass given is 250 kilograms. The height above the datum, notice the datum we've taken here is the top of the pile. That's the lowest point in our system in this case, and that's 8.5 meters. So the potential energy is simply mgh. So we multiply the mass by the gravitational acceleration, which is 9.81 meters per second squared, multiplied by the height above the datum, 8.5 meters. So the potential energy is 20,846 joules, or 20.85 kilojoules, rounding to 4 significant figures. Here's exercise 4 for you to undertake. If a 30 kilogram mass of bricks is lifted 500 millimeters above the ground, we've got to calculate the potential energy of the mass relative to the ground, so the datum is the ground. I'd encourage you to attempt this question. The answer is shown as 147 joules. A solution is shown on the following slide. Exercise 4, the solution. We have our mass of bricks of 30 kilograms raised 500 millimeters above the ground. Notice I've changed that into meters here. It's 0.5 meters. We must use meters in our calculations. So the potential energy is simply mgh, 30 kilograms multiplied by 9.81 meters per second squared, multiplied by the height of 0.5 meters. Be careful there, 0.5 meters. That gives us a value of 147 joules. Our second form of mechanical energy is kinetic energy, energy of motion. Now, a simple definition of work outlined previously considers the force F and the distance S. However, this does not exclude the possibility that the body was actually in motion, having some velocity, say u, at that time when the force was applied. If the velocity is changed from u initial velocity to v final velocity after the body has travelled some distance, labelled s, in a line of action of the force, then it's deemed reasonable to expect that the work done, F multiplied by s, could be expressed in terms of the velocities v and u. As the force applied F is constant, Newton's second law of F equals to ma, we looked at in a previous presentation, states that the acceleration must also be constant. So from the equations of motion that we generated previously, related to constant motion in a straight line, one equation derived is shown below in terms of u, v and s. And this was v squared equals to u squared plus 2as. If you're unsure where that equation is derived from, I encourage you to review a previous presentation related to linear motion where these equations were derived from a velocity time diagram. All we're going to do now is slightly manipulate the equation algebraically to form what's known as a kinetic energy term. So taking the above equation and rearranging it, in other words subtracting u squared from both sides, I can write the above equation now as 2as is equal to v squared minus u squared. If we multiply throughout by half m, so both sides multiplied by half m, on the left hand side I get mas, so the half multiplied by 2 is cancelled. I get mas equals to, on the right hand side multiplying by the half m, I get a half mv squared minus a half mu squared. We know from Newton's second law that force is equal to mass times acceleration, so on the left hand side I can replace the ma here with the f shown here. So on the left hand side I can have f multiplied by s is equal to the half mv squared minus half mu squared. So Fs is the work done when the velocity of an object changes from velocity u to v. And the half mu squared or half mv squared terms are known as kinetic energy and relates to the energy a body possesses due to the fact it's in motion. So again, considering our car rolling down a slope analogy, the body or the car would be exhibiting kinetic energy. So in other words, an object having a mass m and having motion velocity v has kinetic energy. In kinetic energy, Ke is defined as a half mv squared. And just note for reference that the half multiplied by the mass multiplied by the v squared can also be written as mv squared upon 2. In other words, multiplied by a half is the same as dividing by 2 here. Sometimes the mv squared upon 2 is slightly easier to transpose for some students. So exercise 5, got 30 kilograms mass of bricks, impacts the ground with a velocity of 3.13 meters per second. We've got to this time find the kinetic energy just before impact, and that's the scenario here. We're just about to impact the ground. What is the kinetic energy and given the mass and the velocity on impact? That's again shown in the brackets here. I'd encourage you to attempt exercise 5, but a full solution is shown on the following slide. So here's the solution to exercise 5. Our 30 kilograms of mass bricks impacts the ground with a velocity of 3.13 meters per second. So the scenario here is that the mass of bricks are just about to impact the ground. So to work out the kinetic energy on impact is simply the mass multiplied by the velocity squared divided by 2. So 30 multiplied by the 13.13 squared divided by 2, so the 147 joules. We're now going to work through a series of exercises. Exercise 6. If a drop hammer, shown in the sketch, that's basically this lump of metal here, has a mass of 50 kilograms and is raised 1500 millimeters above a forging, we've got to calculate the potential energy in the drop hammer. The answer is shown here in terms of Newton meters. I'd encourage you to start the presentation and attempt this exercise, but the full work solution is shown on the following slide. Here's the solution to exercise 6. Our drop hammer is shown here, having a 50 kilogram mass. It's raised 1500 millimeters above the forging. I've changed the height from millimeters to meters, so 1.5 meters above the forging. And I've taken my datum as the top of the forging here. So to work out the potential energy, it's simply mgh. Mass is 50 kilograms. G is always 9.81. In this case, the height is 1.5 meters. So the potential energy of the hammer in its position 1.5 meters above the forging is 735.8 joules. Exercise 7. A constant force of 1 kilonewton propels a vehicle of mass 750 kilograms over a distance of 0.5 kilometers. We've got to calculate A, the work done, and B, the final speed if the vehicle commences from rest, in other words, is stationary. The answers to part A and B are shown in the brackets here. I would encourage you to start the presentation and attempt exercise 7, but the full solution is shown on the following slide. Exercise 7 solution. So we've got a constant force of 1 kilonewton. I've shown that as F here, of 1000 newtons. Propels a vehicle of mass 750 kilograms. It's my vehicle of mass 750 kilograms over a distance of 0.5 kilometers. Again, be careful with the units. I'm showing my distance here, symbol S, as 500 meters. So first of all, we need to calculate part A, the work done. So work done is simply the force multiplied by the distance. Don't forget, we're assuming the force of 1000 newtons is constantly applied over the distance of 500 meters. So force times distance, that's 1000 newtons times 500 meters. So 500 kilojoules is the total work done. To calculate the final speed of the vehicle commencing from rest, so initially the velocity was 0, we've got to find the final velocity. We will make the assumption here that all the work done on the vehicle goes directly into producing kinetic energy. In other words, we're going to ignore any friction losses in this particular case. So part 2, we're finding the final velocity, that's symbol V. We're going to assume here that all of the work done transfers into kinetic energy. So from the formula, Ke equals mv squared divided by 2. We know that Ke is 500 kilojoules from the first part of the question, so we can rearrange our equation to make V the subject. So multiply both sides by 2, divide both sides by m, and then square root both sides. We end up with velocity V is equal to square root of 2 multiplied by the kinetic energy divided by the mass. Inserting the figures into our equation, the velocity is 36.5 meters per second. Exercise 8. At the instant of striking, a hammer of mass 20 kilograms has a velocity of 12 meters per second. We're asked to calculate the kinetic energy in the hammer. Exercise 8 is very similar to exercise 5, so I'd encourage you to start the presentation and attempt exercise 8. The answer is shown in the brackets on the right hand side. The solution is shown on the following slide. Exercise 8, here's the full solution. Again, we're assuming that the kinetic energy required is at the instant of striking, so it's just before impact occurs between the hammer and the object it strikes. Given the information in the question, the kinetic energy is calculated from the half mv squared formula we've used before. The answer is 1440 joules. Exercise 9. A vehicle of mass 1.1 ton, be careful with that piece of information, has a velocity of 15 kilometers an hour. Again, be careful with that piece of information. The velocity is reduced to 10 kilometers an hour. We've got to determine the change in kinetic energy. And the hint in the question is to convert the velocities from kilometers an hour to meters per second. We reviewed that conversion in the presentation on linear motion. Again, I'd encourage you to start the presentation and solve exercise 9. The answer is given here in the bracket. Exercise 9, here's the full solution. So our vehicle of 1.1 tonne, be very careful with that piece of information. We have to convert that to kilograms, as kilograms is a base unit in the SI system. So the mass of the vehicle is 1,100 kilograms. Its initial velocity is given as 15 kilometers per hour. So remember the conversion from the previous presentation. To convert kilometers into meters, we multiply the numerator by 1,000. And to convert hours into seconds, we multiply the denominator by 3,600. There are 3,600 seconds in an hour. And we do that for both initial and final velocities. That's my u and my v. The question then wants us to find the change in kinetic energy, because the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. So using the symbols, that's mv squared upon 2 minus the mu squared upon 2, my calculations. M in the numerator and 2 in the denominator are common, so I could factorize the equation on m upon 2. And in brackets I would have my v squared minus u squared. And then inserting the values, I can calculate the change in kinetic energy. Just notice the change in kinetic energy is negative here because the vehicle is slowing down. So it's negative 5,305 joules. So that's energy that has been taken out of the system, maybe in braking forces, aerodynamic friction, etc., etc. Exercise 10. A 40-ton lorry is travelling along a level road, a horizontal road here, with a uniform velocity of 30 meters per second. The lorry is brought to rest in a distance of 0.15 kilometers. We've got to calculate the braking force required to bring the lorry to rest. We're told to ignore any frictional effects. Again, I would encourage you to attempt this question. I would suggest on your page on the left-hand side, sketch the lorry travelling at 30 meters per second, and then on the right-hand side, sketch the lorry, but now it's come to rest. You've got to calculate the braking force, so that means there must be a force opposing the relative motion in this case, so you can add the force to the diagram, and it'll be the work done by the force that will bring the lorry to rest. I'd encourage you to stop the presentation and think through that question, slightly more complicated scenario. The answer is given here as 120 kilonewtons for the braking force, but a full work solution is shown on the following slide. So exercise 10, I have a 40-ton lorry. I've changed that to 40,000 kilograms here as the mass of the lorry. It's travelling initially with a velocity, I've labelled that u, of 30 meters per second. And it's brought to rest, so the final velocity v is 0, in a distance of 0.15 kilometers. So I've showed that here, s, my distance, as 150 meters. Note we're going to ignore frictional effects in this particular question. So I've drawn a sketch here of my problem. I've called this position 1, where the vehicle is travelling at 30 meters per second, and in position 2, 150 meters further on the level road, the velocity is 0. So I'm going to commence by constructing what's termed an energy balance here. So my initial energy and any work put into the system is equal to my final energy and any work out of the system. That's called an energy balance. On the left-hand side, I could have initial potential energy, initial kinetic energy, and work into the system. And on the right-hand side, I could have final potential energy, final kinetic energy, and work out of the system. Now, this particular case, because we're on straight and level road here, then if I take my datum at the road surface here, then there'll be no change in potential energy between position 1 and position 2. So there'll be no initial potential energy to concern us and no final potential energy to concern us either. If I consider position 1, I know that I have a 30 meters per second velocity here, so I must have some initial kinetic energy. So I've definitely got kinetic energy here. But if I consider position 2, we know it comes to rest. My final velocity v is 0. So there'll be no final kinetic energy. Is any work being done as the vehicle moves from position 1 to position 2? Well, there's no force applied to the vehicle at position 1, pushing it from left to right, so there can't be any work into the system. But we know there is work out of the system because we've got the braking force that will be assumed constantly applied over the distance of 150 meters. So we definitely have the work out of the system due to the braking force. We're ignoring any frictional effects here. So my solution simplifies purely to initial kinetic energy due to the vehicle's 30 meters per second velocity initially, with work out of the system on the right hand side of the equation. So that's what's called an energy balance. If I now put the equations in for the energy balance, on the left hand side I have mu squared divided by 2. On the right hand side I have FB, I've called it FB for the braking force, multiplied by S. So rearranging the equation and solving, FB is equal to mu squared divided by 2S. I just simply divided both sides by S. And then inserting the figures given in the question, the 40,000 kilograms for the mass, the initial velocity is 30 meters per second squared, and that's divided by 2 multiplied by the distance in meters, 150 meters. So that evaluates to 120 kilonewtons. So in that exercise, I tried to apply the full energy balance and see how it's simplified down in this case to simply 2 terms, one on the left hand side, kinetic energy, and one on the right hand side, work out of the system. Exercise 11. A lorry which has a mass of 5 tons jumps its brakes and rolls down an incline which is 3 degrees to the horizontal and 0.5 kilometers in length. When it says the jump, the brakes is trying to indicate is starting from rest at the top of the incline. We're asked to determine the velocity of the lorry when it reaches the bottom of the incline. Again, we're ignoring any frictional losses that might occur. Note for reference, 1 ton is 1,000 kilograms. There's a hint in the question that we might need to use basic trig here to calculate the vertical height through which the lorry falls during the motion. I would encourage you to start the presentation, attempt this question. I would suggest to start by drawing a sketch on the left hand side of your page of the lorry at the top of the incline, and then on the right hand side draw a sketch of the lorry at the bottom of the incline. If you take your datum at the bottom of the incline, you can then consider what energies you have when the lorry is at the top of the incline and what energy the lorry will have at the bottom of the incline. The answer for the velocity is shown here, but notice it's stated in kilometers per hour. The full work solution will be shown on the following slide. So exercise 11, here's our lorry, the top of the incline. I've called that position 1 here. It's a 5-ton lorry. I've converted that to a mass of 5,000 kilograms. The lorry jumps its brakes, so that means the initial velocity was 0 at the top of the incline, and it rolls down the incline, which is 3 degrees to the horizontal here, and is 0.75 kilometers in length. So my S dimension here is 750 meters. We've got to determine the velocity of the lorry when it reaches the bottom of the incline. So what's the V in this case when a lorry is at position 2? As the question hints, we will need to calculate the height h shown here for the fall of the lorry as it moves from position 1 to position 2 on our incline. So again, as in the previous exercise, I'm going to commence by stating an energy balance. So on the left hand side of my energy balance equation, which relates to position 1 here, I've got my initial energy and any work into the system. is equal to, at position 2 here, my final energy and any work out of the system. So essentially this time on the left hand side, the only energy I have is potential energy. The fact that the vehicle here is this height h above my datum. Notice I've taken the datum at the bottom of the incline. I always encourage you to take the datum at the lowest point of the system you're considering. So in this case it's the bottom of the incline. I have no kinetic energy on the left hand side of my equation when the vehicle is at the top of the incline, because there's no velocity of the vehicle as it rests, as it jumps its brakes. There's no work being done between position 1 and position 2 here. There's no external force applied to the lorry, pushing the lorry down the incline. It's purely moving down the incline under gravitational effects. At the bottom of the incline, at position 2, the only energy I have now is kinetic energy. If the vehicle is on the datum, which it is at position 2, then there's no potential energy. There is kinetic energy because we have a velocity. We're trying to calculate the velocity, so there must be a kinetic energy. And there's no work out of the system between position 1 and position 2, as there's no frictional forces to consider that oppose the motion. So here's the full work solution. So potential energy is mgh on the left-hand side of our equation. Kinetic energy is mv squared upon 2 on the right-hand side. Just notice that in this case the mass terms cancel, so we don't actually need the value of mass in this particular question. So now gh on the left-hand side is equal to v squared upon 2. Then simply just transposing the equation to make v the subject, we first of all multiply both sides by the 2 and then square root both sides. So finally, velocity at the bottom of the incline is the square root of 2gh. Obviously we need to find the value of h, and that's calculated on the left hand side of our screen here. We go back to the original diagram. We essentially have a right angled triangle here, trying to find the opposite side to our angle, trying to find h in this case, and we know essentially the hypotenuse side, which is 750 millimeters. So from our SOHCAHTOA we reviewed in a previous presentation, we can see that the sine of the angle, in this case 3 degrees, is equal to the opposite side, that's h, divided by the hypotenuse, 750. So rearranging the equation, the height h of our incline is 750 multiplied by the sine of 3 degrees. So height h is 39.25 meters in this case. So now we've got the value to use in our formula, 39.25 here. Evaluating, the velocity at the bottom of the incline is 27.75 meters per second. And if you convert that to kilometers an hour by multiplying by 3,600 and dividing by 1,000, that's about 99.9 kilometers an hour. So there's our full solution for exercise 11. Here's the bibliography used to help generate the presentation. I hope this has been of interest to you. Thank you for viewing.